And we're on! Hello and welcome to PICO-8 live coding with Jobe. Sorry for the poor frame rate with the webcam, but I'm pretty sure you're not here to watch my face anyway. So, so about myself, well, I'm not a terribly experienced coder. I just started coding with PICO-8 2 years ago, but I think that I managed to get onto some pretty advanced stuff by now, which brings us to the PICO-8 itself. If you're not... Oh, okay, music may be a bit loud for my voice, thanks for the input, Procyon. I'm bringing it down a bit. Okay, yeah, so... I think I'm being able to do somewhat advanced stuff with it so far, which brings us to PICO-8 itself. PICO-8 itself is a fantasy console, which in this case means a Lua virtual machine that has aesthetic and technical limitations. Kind of similar in some ways to an old school platform, and I think it's one of the most approachable platforms for a newbie coder interested in demo coding. So I'm gonna try to keep this broadcast newbie friendly, beginner friendly. I'm gonna try to keep it in stuff that can easily be grasped if you have an understanding of really basic programming concepts like for loops. Then you should be able to follow along. But let's get cracking. Okay, so first we're gonna do the basic structure of the program, which consists of three system functions. They are function init. This thing here obviously is called when the program starts, and for now we'll just set a frame counter here, f equals 0. We could use PICO-8's own time function to keep time, but I prefer to do it this way myself. Then we're getting to the update function, and when we call update 60 is gonna be called, it's gonna try to call it 60 times per second. If we have an update 60 here in the program, the function, then it means it's gonna target 60 FPS. That is not the default frame rate for PICO-8, but it's a frame rate that I'm gonna try to aim at, and we're gonna put a... Okay, so every time update 60 is called, it's gonna increase f by 1. And then we're gonna have our draw loop. So this is obviously where most of the interesting stuff happens. So now we should have a working program. Oh yeah, I need to save it obviously. Let's load it, and it runs. Of course it doesn't do anything yet, but we're gonna start with a very simple effect. We're gonna start with a star field, and we're starting with the star field because I'm gonna be able to show how 2D rotation works. So first of all, let's have an array called star field, and also let's set a size for the star field in stars. Stars amount equals, let's start with 50, and then let's create our stars, our initial, what we're gonna see on the first frame. We're gonna do a for loop of I equals 1, and it's gonna go to 50 stars amount, and every every time, on every I loop, it's gonna call the function create star and gonna give it an R&D, let's say 50. And now what this does, now we're gonna do the create star function, and our entry, and we're gonna enter the variable, and we're gonna call it distance. So this is gonna be the distance the star has traveled, and oh yeah, we need to actually do this. Yeah, this is the add is going to add function is going to add a new index into our star field array. So in our create star function, we're going to create an array for the star, and we're going to determine the direction for which this star that it creates, where it's going to. We're going to call this variable theta, and we're going to have it a random value between 0 and 1. And now we're going to get to the rotation thing. So this weird thing here is the 2D rotation matrix. It might look, if you're not familiar with matrices or graphics coding, it might look a bit weird, but basically this is because PICO-8 does not, it doesn't have rotation maths built in, so we're gonna need to do it ourselves, but fortunately it's quite simple. So basically it's just, if you want to rotate a point, then the x of the new point is gonna be x times cosine theta minus y times sine of theta, and the new y is gonna be x times sine theta plus y minus cosine theta. We're going to copy this here. Let's copy this here and turn it into a comment, so we are gonna have it here. So with this theta, we're gonna be able to determine the direction of the star on the screen. So star direction x is going to be x times cosine theta. So if we're going to assume that x is 1, then it's just gonna be cosine theta, and minus y times sine theta, but we're gonna assume that y is 0, so we're not gonna be needing it here. And direction y is going to obviously be sine theta. Okay, then the stars are gonna need a speed, so let's start with 0.5. It's gonna be the lowest possible speed that the star can travel at, plus random 0.5, which is gonna be the top speed over 0.5 that the star can travel. So, and once it has determined these things, it's going to return star. And now let's just see that I haven't done any typos or anything. Oh, obviously I have done it. Okay, yeah. Okay, so where is it done? Yeah, for loops need a do, obviously. So yeah, it still doesn't do anything, but now we have a star field. And now let's do a draw star function. And it's gonna say get the star as the value that it receives. So now we're going to do this for for each, for star in, sorry, I'm a bit nervous. Okay, so we're gonna do a for loop. This means that it goes to the whole star field array and treats every entry in it as one at a time as variable star. So we're gonna do draw star star, and then we're gonna get here, and now we're going to determine the distance, the distance from the screen center. So that's going to, oh yeah, I forgot one thing here. Obviously, star distance is equal to distance. So now screen distance is going to be some value, let's say 1.05 to the power of star dot distance. If we do it this way, we're gonna get sort of like an accelerating motion for it. And then we're gonna do pset. This is the simplest graphics function in PICO-8. So it just draws a pixel. So screen distance times star direction x, screen distance times star direction y. And unless I've messed something up, we should get something on the screen now. Let's see. Yes, so this, you've noticed that two things. A, it's pretty small, and B, it's all in the top left corner. This is because, of course, 0 is in the top left corner. So what we're gonna do now is we're gonna use the camera function. This adjusts everything that the PICO-8 graphics functions do. So this is going to move all pixels 64 to the right and 64 down. The resolution of the PICO-8 screen is 128 times 128. So now it should be in the center. Yes, it's still pretty small though. So what we're gonna do now is we're gonna adjust this value until we've filled out the whole screen. So let's try 1.1, and it's better. Let's see if it can be something smaller. No, 1.1 is good. So now it's better. And we're also going to want our stars to move. So before our loop here, we're going to do another. So star. No, wait, we're not going to do it here, obviously. Star distance, and we're going to add star distance, and we're going to add the star speed into it. So let's see if this works. And it works, but obviously we're going to run out of stars pretty soon, so we're going to do another loop to find out if the stars have escaped the screen. So before this loop, we're gonna check that if the first entry in the star field, if the distance is over, say, 80, then, no wait, star field I, of course, not star field 1. So then it's going to call the create star function, and we're gonna enter something like 1 as the starting distance. So let's see what we have now. We have a typo or a syntax error somewhere. Star field I. Okay, what did I? Obviously I did it all again in the init. So I do stuff like this all the time. So sorry about that. So yeah, now we have a star field here. And now let's see how many virtual CPU cycles this thing takes now, because PICO-8 has a virtual cycle limit. Everything you do has a virtual cycle cost, and if you get over 100% CPU load, then it drops the frame rate. So we're gonna use a print stat1. Stat1 is the function, system function. Oh yeah, we're gonna reset camera before we get there. Stat1 is the system function that shows us how much CPU power we've used. And we've used about 12% so far. Don't you have to multiply the theta in create star by 2 pi? Actually no, because the sign functions in PICO-8 take a value between 0 and 1. So that's the range we're aiming at. So yeah. No, where was I? Yes, and now we're gonna see how huge this is gonna the CPU load is gonna get once we increase the stars amount to 500. And now we notice that we are over 100% CPU load. We've dropped to 30 FPS, and we're not gonna want to drop to 30 FPS for just a simple star field. So let's get back to 50. So this is our initial effect. We could still adjust the speed a little bit so it will look less hectic. Yeah, and I think we're gonna be able to go to something like 100 stars, and now it looks nice, I think. So we're gonna go with this. So one more. Yeah, I'm actually going to increase the starting distance. So do something like 7, so it doesn't show a huge clump of stars in the center of the screen. I think it's better now. So now let's do something else. Let's go with a plasma effect, I think. And as you can see, I've already PICO-8 has a built-in sprite editor. And you've seen I've already drawn 8 sprites. These are going to be the tiles for our plasma effect. We're not going to be able to do a full plasma with a whole screen where we're going to calculate a value for every pixel, because the virtual cycle limit is just going to get filled by that. But we're going to do a tile plasma using this tile set of 8 sprites, and let's start with creating a function for that. Let's put it here because I don't think we're touching the star field function anymore. So we're gonna do 2 loops. So we're gonna start with for x equals 0 times 15. We're going to have it run this amount because all the sprites are the sprites are 8 pixels wide, so we're gonna be able to draw 16 of them in a 128 wide screen. Yeah. And then we're going to do another loop inside that from I equals 0 to 7, let's say like that. And then now we're gonna have a grid of 16 times 8. And now we're gonna do a function, a variable called value, and this is gonna be the, let's say, brightness of the plasma in that space, and basically it's gonna mean which of the 7 sprites we're gonna draw. As you can see, these are numbered from 0 to 7. Also, we're going to clamp this is not necessary yet, but it's going to be necessary once we start doing functions for the plasma. So we're going to make sure that the value is between 0 and 7, and we're going to make sure that it's an integer. So yeah, now it can't be like -3 or 15 or 5.7 or anything. And now we're going to draw our sprite. So we're going to use sprite, and we're going to use value as the number of the sprite, and we're going to draw it at x times 8, and that's going to be the x value, and we're going to be drawing it. The upper corner of the plasma effect is going to be at 32 pixels plus y times 8. Now, let's see what this time I noticed that before of the syntax error, and we're going to add our draw plasma call here. So let's see what I've messed up this time. Unclosed function of line 33. Oh yeah, we need to close the draw plasma function as well. So now we have a beautiful grid of red squares. Not terribly interesting, but let's do something else with that. Now let's do something with our value. Let's say we started at 4. Now we're going to add something to it based on which frame we are in. So let's add 4 times sine frame counter times 0.01. So now something should happen. And it's still not a plasma, but at least it's remotely more interesting than previously. Okay. Everyone with me so far? And now let's do something a bit more plasma-like with it. So let's actually add something relating to where on the screen it is. So to this function here, let's add plus x times 0.05. So now you'll notice that there's this kind of pattern now. So there's a sine value based on the x value of where we're drawing. And we can do more stuff with that. We can adjust this multiplier, let's say, judging by the cosine of y times 0.01. Let's see what's going on now. What's going on now is unclosed parentheses. And okay, well, we're gonna have to make this larger Okay, we're gonna have to make it smaller. And let's do something with this value. Okay, now it's looking weird. Let's just adjust this a bit more. Now it looks a bit more like a plasma. And we can still add some more operators to it. So let's add 3 times the cosine of y times 0.01. And it's actually not this much. Let's make the frequency a bit higher. Let's make the frequency a bit lower. And let's have it scroll about a bit. So now it looks a bit more like a plasma effect. So basically we can experiment with these values and see what we think looks pretty. So let's just add one more thing here. And yeah, now we have this is something that I might call a plasma effect. So yeah. And now we see that we can optimize things here. There's no point really in doing things that are, for example, related to the x value every time, like 7 times without the x changing in between. So no, actually all our modifiers are dependent on. Well, let's do it this way. Let's change this to x so I can show what I mean. So now the plasma effect looks like this, and our CPU load is about 42%. But of course it doesn't have to calculate that x value that often, so we can move it here. Plasma function 1 equals this thing, because this is not dependent on y, which is the inner loop. And let's see what that does to our CPU load. Probably not a lot, but it should decrease it a bit. Well, I don't think it reaches like 42% anymore, so it's slightly lower. So that's our plasma. Next, what we're gonna do, okay, let's forget about our plasma for a while, but we're gonna be returning to it later. Now, if you've seen any of my demos, you'll know that this function this effect right here is something that I have an obsession with. So we're gonna draw a twister. So we're gonna start our draw twister function with moving the camera down. We're gonna move where we draw things, we're gonna move it down by 64 pixels. Okay, we're gonna start like pretty simply. We're starting with a rectangle that is from the left side of the screen to the right side of the screen, and from minus 32y to 32y, and we want our rectangle at this point to be red. Why do we not? Oh, we do not have a rectangle because we are not calling the function. Okay, here we have a... Oh yeah, and we're gonna have to remember to actually make sure that our stars are going to be white and not red. And now we have a rectangle. We have a perfectly not moving or twisting about anyway kind of rectangle. So let's make it move somehow. So we're going to have a face. We're going to start by doing one side of the twister. We're going to have 4 sides of it, and we're going to calculate the phase of rotation for that side, and it's going to be dependent on the frame counter. So let's say it's 0.05 times frame counter, and y1, which is the upper corner, is going to be... Okay, we're going to determine the size of the twister. Let's say it's going to be 32 pixels. And what the upper corner is going to be phase times that. The lower corner is going to be that times phase plus 0.25, because remember our phase is going to go from 0 to 1, so we want the next corner to be determined by the current phase plus 0.25. So let's see what happens now. We've replaced this one y1 and this by y2. Now it should be moving about a bit. And we have forgotten to reset the camera. Also, we have forgotten that this is supposed to be a sine function, obviously. So now it should look better. And sine is written without an e, of course. And it spins about a bit too fast, so now we have one side of the twister right there. But we're only gonna want to draw it when it's actually facing the camera, so we're only going to draw it if y1 is smaller than y2. So let's see how that looks. Yeah. So next thing we're going to do is do all the other sides. So we're going to do a loop from 0 to 3. And we're going to want to have every other side of it going to be in a different color. So, for example, if I is 0 or I is 2, then we're going to change the color to 9. Alright? And our phase is going to be that value plus I times 0.25. So let's see what happens now. Do. We're missing a do. Okay, so now we have a sort of like a box thing that spins there. It's still a twister, but we're getting there. Shouldn't the create star loop be in the update function? Actually, yeah, that actually would be a better idea. That's a good point. Ideally, everything that we want to run like 60 times per second, even if the draw loop doesn't run 60 times per second. It should be in the update loop. So yeah, that's a good point, Serix. So yeah, you should do it like that. But we're not going to be running out of cycles here, so I'm not going to do it like that right now, but you should. But now we're going to turn this bar into an actual twister. So we're going to do a loop with 0 from x is 0 to 127. And we're going to replace this rectangle fill function with a line function that is going to draw a line with x value x, obviously, and it's going to be from y1 to y2 in that direction. Yes, I keep mixing which is vertical and which is horizontal. English is obviously not my first language, but yeah. So now to make it somewhat twisty, let's make the x value have an effect on what the phase is. So let's see what happens now. What happens now? Well, this was predictable, but okay. So now it looks like a weird kind of candy cane or something. So let's make this the frequency a bit lower. So yeah, now it looks a bit twistier, and we can also modify this by, let's say, sine of the frequency counter times 0.0. Let's go with this and see what it looks like. And it looks really weird. What am I doing wrong? What am I doing wrong, actually? Well, still a bit weird, but oh, let's modify this value so it's not gonna be a full 1. And now I think we could make this larger. Oh, that's okay. Now it's twisty. This is a twister, and it's a bit monocolored, but let's actually, I think we could add, wait a second, what happened to, okay. I think we could add some shading to it. Now I'm going to get to show you the fill P function, with which we are going to be able to do patterns. So basically you can use fill P to set all graphics functions so that they don't fill every pixel. And we do it by setting a binary value with 16 digits that comprise a 4x4 grid. So if we could do a grid that looks like this, for example, so that's gonna be a sort of like a square grid pattern, and we're gonna want to make sure that the fill P is reset after the whole twister loop. So what we have now looks like this. So yeah. And I've actually prepared an ordered dither pattern here, which we can use to shade this twister. So yeah, all of these are again 4x4 grids. We're gonna copy this dither pattern to our init function, wherever it may be. Here it is. And we're going to calculate the brightness here, judging by the difference of y2 and y1. So brightness is y2 minus y1, and because we're going to be getting the value from an array, we're going to want to clamp the value between 1 and 17. Remember, in Lua array indexes start at 1, and of course we're going to want to make sure that the brightness value is an integer. And we're going to do fill p dither, and we're going to get value index brightness from the dither array. Let's see what that looks like. Okay, it looks the other way around. This is because we normally have 16 colors on screen, maximum simultaneously. But how the fill p works is that it draws the off bits from the low bits of the color value and the on bits from the high bits. So we can have a value of. So sorry, I'm getting a bit confused, but you'll see what I mean in a while. So we multiply these color values by 16. And now it looks better. And we can still make it a bit darker by decreasing, let's say, 7 from the brightness. And now it looks like that. And if we don't want to fade it to completely black when it shades out, let's see, we could say that the color 8, which is red, it could fade into color 2, and then color 9, which is orange, it could fade into color 4, which is brown. And now let's see what that looks like. So now we have a nice twister there. Yeah. And now we've done a twister and we've done a plasma. But how about we combine the two? And now I get to show you one interesting thing that you'll need to know when you're coding demos for PICO-8, which is using the memory. The PICO-8 has a memory, addressable memory, and you can use it to buffer things. So for that you use the memcopy function. So basically the PICO-8 has 32 kilobytes, I think that was 32 kilobytes of addressable memory, which you can poke, copy however you want, and sometimes it just results in weird things, like for example your music getting garbled and such. But if you know what you're doing, then you can use it for example, manipulate the sprite sheets. So as we see here, these are some interesting memory areas when you're coding demos. So this area right here is the screen data. Obviously, like whenever you poke something, whenever you change a memory address, memory value here, something happens on the screen. And from 0 to 1FFF hexadecimal value, it's the sprite sheet. So basically, we can copy everything from the screen to the sprite sheet, for example. Oh yeah. Oh, sorry. Yeah, good point, Procyon. I'm sorry about that. Oh yeah, now we have the editor. Yeah. So screen data range is here, which I explained. This is everything that you see on screen, and the sprite sheet is here. So let's see what that means. Let's put the mem copy. Our destination is going to be the screen memory. Our source is going to be the sprite map, and we're going to copy 8 kilobytes of data from there to the screen memory. And now as you see, we just have the sprite map there. But we can also do that the other way. So let's copy the center of the screen. 64 lines from the center of the screen to the center of the sprite map. And let's actually do that after we've drawn a plasma. We're actually going to want to do the plasma before we've drawn the stars. And after which we'll clear the screen. And again, at the end of the loop, we're going to have it copy the sprite map to the screen. And now it looks like it shouldn't look like this. Oh yeah, well, the source has to be 6800. So this means that it starts copying from line 32. So yeah, now we see this is our whole sprite map, and we can see that our plasma effect is in our sprite map. So what does this mean? It means that now let's do another version of our twister effect. Let's just wastefully copy it here. Yeah, you don't want to be repeating code, but for the purposes of this demonstration, we're going to repeat code. And draw twister textured. So we no longer need the color functions. We no longer need the fill pattern because we're going to draw this in a completely different way. We're going to be using SSPR. That's the other way to draw stuff from the sprite map. And the difference between SSPR and SPR is that SPR draws one sprite from the sprite grid. It's always going to be 8 times 8, but SSPR is more flexible. We can draw any rectangular area from the sprite map. So the first two values are going to be the top left corner of the area from the sprite map that we're going to be drawing. So it's going to be X and 32. Then the next two are going to be the width of the source. So that's going to be 1 pixel wide, 64 pixels downwards. Now the next two values are going to be the destination, where we draw our line. So it's going to be X and Y1. And now the size of the area, this is where we're gonna be able to show the scaling abilities of SSPR. So we're gonna draw the area as 1 pixel wide, and the height of it is going to be y2 minus y1. Now let's add our draw twister textured function here. Let's see what we've done wrong this time. We've actually done nothing wrong. It's transparent, but we can fix that with a... because normally when you draw sprites, 0 color, that's black, is transparent, but let's set it so that 0, we're going to use palt function. This is a built-in graphics function that adjusts the transparency of all the colors. So let's say that 0 black, its transparency bit, we're going to set it to false. And now it looks like this. So looks a bit better now. Let's do it. Metastage is asking what is Yobe. Well, that's me. That's my demo scene handle. So yeah. And yeah, I maybe should have written it there. But yeah, that's just my kind of nickname in the demo scene circles. So now let's get our editor back on the screen. This still looks a bit boring because now every side is just the same red. So let's do this. If I equals 0 or I equals 2, so now we're going to change this palette a bit. So this is going to adjust the color switches draws, because these are the sprites use colors 8 and 2. But let's say we want the other sides to be yellow and brown. So every other side we're gonna be changing 8 into 9 and 2 into 5. No wait, 4. Was it 4? Yes. And we're gonna add a palette reset function here to make sure that it resets the palette, because otherwise it's just gonna change this palette once on side 0 and then just draw everything with that palette afterwards. And because I think the pal function resets the transparency bit, so we're gonna have to move this here. Let's see what we have now. We have a missing then, because why wouldn't we have a missing then? And yeah, now we have a textured twister. Okay, I think it's looking pretty nice. It's a pretty nice effect. And now we still have time to show you one thing, and that's going to be a wireframe cube. So let's start with defining our cube in the init. So we're going to be defining the vertices of the cube. So these are all going to be 3-dimensional coordinates. So it's going to be an array. So the front face of the cube, so basically it's going to be -1x, -1y, and -1z. No, this is actually going to be the back face of the cube, of course. And this is one corner of the back face. Now another corner and another corner and one more corner. So this, now we have a square. And we can just copy this line to make the other side. And because this is going to be a wireframe cube, it's not going to have polyfillers or anything, we do not have to worry about whether our vertices are clockwise. If we would fill the polygons, then that would be an issue, but right now that we're not worrying about that. Now, let's make another array with the lines of our cube. So let's start with our back face. It's going to be drawn. So these all have a obviously index number. So this is vertex 1, vertex 2, vertex 3, vertex 4, and so on. So our lines of our back face are going to look like this. So that means there's a line drawn from vertex 1 to 2, vertex 2 to 3, and so on. Our front face is going to be the same, except starting with vertex 7. Okay. And now we're going to need to connect the faces. So we're going to draw a line from 1 to 5, 2 to 6, 3 to 7, and 4 to 8. That there is the 12 lines. Those are going to comprise our cube. Now, these are three-dimensional coordinates, but of course PICO-8 doesn't know what to do with three-dimensional coordinates. So now I get to demonstrate the three-dimensional rotation math. This is a bit more complicated than the two-dimensional rotation we covered earlier, but only a bit more. So if you were able to grasp the two-dimensional rotation matrix thing, you should be able to grasp this. So let's copy this thing, which I prepared earlier, and we're going to do a draw cube function. And actually I wasn't supposed to do this yet. Sorry about that. I'm getting ahead of myself, but we're gonna need this later anyway. So I've prepared two functions which we're gonna need. Flatten, point, and round. Let's copy these here. So I'll explain what these do. So flatten point is a function into which we're going to feed an x value, a y value, and a z value. And it's going to be converting them into an x value and a y value two-dimensionally by multiplying them by half the screen resolution, dividing it by z, which is the distance from the camera, and then adding 64, which is going to mean that 0 is going to be at the middle of the screen, and it's going to do the same for y. And this is a very rudimentary way to project the 3D points into 2D space. It has no it has no FOV controls or anything, but it'll do at this point. So we're going to draw the cube. So for cube line in all cube lines do. So x1 is going to be the x1 and y1 are going to be flatten point, flatten point, I'll get there eventually. Now, flatten point, and we need to send it 3 values, so those are going to be cube vertices, cube line 1, 1. Okay, this is a bit convoluted, but basically it means that we're taking from array cube vertices, we're gonna take entry that is number cube from the cube line. So basically every cube, sorry, I shouldn't touch my face, but yeah, it takes the value from here, so no 1, and that means this vertex, and it takes the first value, i.e. the x value. So basically, yeah, it looks weird, but that's how it works. And we're just gonna copy this 3 times, so we're gonna get the x, y, and z value from there. And we're gonna copy this and get the other end like this. So now we have starting x values and y values and ending x values and y values. And now let's see what happens when we try to draw a line between those. So first, okay, what we notice that we don't so much have a cube as an x on the screen. This is because of 2 reasons. Everything is centered around 0, so, and 0, the origo is where the camera is, so basically we are now inside the cube. The other thing is that our 3D routines don't really know what to do with points that are behind the camera. They confuse them. So let's add a translation thing here, which is going to move all our vertices. For that, we're going to move the code that defines our vertices into the drawCube function. This resets it every time, and this also means that we get to do things with them each time. So for I equals, from I is 1 to the amount of cube vertices. And now from each vertex, we're going to decrease 4 from the third value, that is the z value, and now we should have the cube not on top of our camera. Let's see if that's right. And what happened is that we've misdefined something. What have we misdefined? Oh, we have misdefined this. So obviously this needs to be 5. So now it should look like a cube. Yes, it is indeed a cube, but it's not a very interesting cube just yet. It's just there. So I was getting ahead of myself earlier, but now I get to do things with this. So our 3D rotation matrices work pretty much like the 2D rotation matrices. So let's rotate this cube around y-axis, i.e. we're gonna be using this matrix right here. And let's define our theta value. Let's have it be something like 0 times 001 times f. Let's have another for loop. Now, we're gonna have a array called vertex. That's going to be the cube vertices array index number 1. Now, let's define our rotation. So let's start with x. So x rot is going to be x, so that means vertex brackets 1 times cosine theta plus vertex bracket 3 times sine theta, and that's that. Y rot is just obviously going to be vertex bracket 2. It doesn't change the y in any way. Z rot equals vertex, so x, actually, it means to be minus vertex 1 times sine of theta plus z, or vertex bracket 3 times cosine theta. And now we're going to replace the original vertex with our rotated values. So let's see what happens now. Okay, it rotates. Slowly, but it rotates. Isn't that amazing? And let's make it a bit faster. A bit slower. And we have a cube that spins around the y-axis. And while we're at it, let's have it spin around some other axis, let's say z-axis. And again, we're gonna wastefully just be copy-pasting code. You don't want to be doing that in a real project, but this is a pretty quick way to go about things here. So let's do the same loop, but with a different speed and with a different rotation vertex. We're gonna be using the matrix. So we're gonna be rotating it around x. So it's obviously gonna be x is just x. Nothing happens to that. Y is y times cosine theta minus z times sine theta, and z is gonna be y times sine theta plus z times cosine theta. Let's see what happens now. Okay, now we have a cube that spins around two axes. Let's look at it for a while. Now what we can still do is we can actually have it spin around that twister. So for that we're gonna need to do something to our translation thing. So let's, at the beginning of the draw loop, let's define some variables which are gonna be the center of where we want our cube to be. So the starting values are going to be x equals 0, y equals 0, and z equals something else, let's say 3. Actually, let's say 4. And we want to rotate those around the x-axis. So we need another theta here. Let's say 0.002 times f. And let's get our x rotation matrix. So our cube x is going to be just what it was. Our y is going to be y times cosine theta minus z times sine theta, and z is gonna be y times sine theta plus z times cosine theta. Now we have a point in space that is just spinning around. So what can we do with that? So let's add them as arguments for our cube function. So now the cube function has these arguments. Where's the cube function? Here, of course. So it's gonna, let's say it receives x, y, and z. Now let's improve our translation thing. So we're gonna just make it so that x is going to be have the plus value that we receive added to it, and so on and so on. So now it's translating the cube in all 3 directions, and of course we need our initial z value to be, let's say we need to decrease 6 from it, so it's not going to be on top of the camera. Now let's see what happens. Okay, now we notice that it moves. It's a bit slow, so let's do it. Let's try this. Okay. Maybe gets a bit too close to the camera, so let's do it like this. Actually, no, we want it to spin around the twister, so we're gonna want the range of motion to be wider. So let's say that the radius of the circle it moves in is going to be 7, and that means that we're going to have to translate it by, let's say, 8.5, so that the circle is not going to touch our camera. So let's see what it looks like now. Yeah, that's better. We could still maybe make the circle a bit tighter. Now let's try this. Yeah, it's better. And we're gonna want our cube to actually spin around the twister. So we're gonna do this thing. We're gonna be calling the function before and after we draw the twister, but with conditionals. So it draws the cube before the twister if cube z is below 0, and if cube z is equal to or greater than 0, then it draws it after the twister. So now we should have a cube that, yeah, now it spins around. Now it spins around the twister as intended. So now it's looking pretty nice. And we still have a little bit of time here, so let's do some funny glitch effects with memcopy. So, oh yeah, and we're not. Let's get rid of this. We don't need it anymore. So yeah, that's our effect. Okay. Hi there, writer. Thank you so much. Yeah, I'm pretty. I think it turned out pretty nice. Now, let's make it uglier and let's do some glitch effects to end with. So, like for example, let's have a loop that runs 10 times. Now we're gonna do some weird stuff with memcopy. So, okay, so our address from where we... Okay, so let's have a random number between 0 and the size of the screen buffer minus 16. So now let's copy. Oh wait, actually we shouldn't do that. We have no reason to do that here. So let's do this is gonna be our destination is going to be in the screen memory area. Our source is going to also be in the screen memory area, and what we're gonna do is that 10 times every frame we're gonna be copying a 16-byte chunk from somewhere in the screen memory to a random position in the screen memory. So let's see what that looks like. And it's missing a do, obviously. So now we have a glitch. Let's make it even glitchier. Let's do that 100 times. Now it's really looking horrible. So let's make the chunk it copies a bit smaller. And now let's increase this and okay, so now it's obviously having a huge CPU load because the frame rate dropped. So let's go back to 100. And this is just an example of a simple experimental glitchy effect you can do with memcopy. But yeah, this is pretty much everything that I wanted to show tonight. Thank you for watching the stream. I'm planning to make another show next week. It's probably gonna be Wednesday at the same time. So it's 6 o'clock in the evening. Wednesday next week. And thanks for joining our stream. And yeah, sorry that you missed it, but hopefully it has recorded the VOD so you can watch it later. And I've also, in case it didn't, I'm also recording it, so I'm gonna be putting it on YouTube. So just search this name from YouTube. That's my channel. I'm gonna be putting a capture of this stream onto my YouTube channel. But yeah, thanks for watching. See you next week, and have a nice evening.